All right, welcome everybody to this week's GOCC. Today we have the pleasure of having Suji Hung from the University of Nebraska-Lincoln, and she'll be talking to us about Newton polytopes of symmetric Grothendieck polynomials. So please welcome Suji.
Um, Thank you for having me. I am very happy to talk about this topic here. Um, and thanks for changing the time so that I can actually give a talk. So this is based on a joint work with Marsh, Baer, Bennett, Terrell, McCabe, Casey, and Julie, and Martha. So we met at GRWC last summer, and then we worked on this project. So to go over, so in here I will just introduce the Newton polytope and the integer decomposition property and reflexivity. So a polytope is you can think of it as higher dimensional polygons. So it's going to be a convex hull of a bunch of points. And what I mean by convex hull is that it's just going to be sum of those points such that the coefficients add up to 1. And the inclusion minimal set is going to be called the vertex set. So you can really just think of it as the vertices of a polygon. And we'll call a polytope a lattice polytope if all those vertices have like integer coordinates. So a Newton polytope of a polynomial is given by the convex hull of those, like the exponent vectors. So, for example, if we let f to be x1, x2, f of x1, x2 to be this polynomial, you can see that this corresponds to, so the exponent vector of this is just 3, 0, since this is the same as saying x2 to the 0th power. So that corresponds to this point right here. So all these terms corresponds to these points, and then we take the convex hull of this, which gives us this polygon. So that's the Newton polytope of this function f. And we say that a polynomial f has saturated Newton polytope if every lattice point alpha on this Newton polytope appears as exponent vector. So this notion was introduced by Monica, Token, and Young in their paper. So if you look at it here, you can see that this 1, 1 is a point on this Newton polytope, but you don't see x1, you don't see x1, x2 in this polynomial. So this example does not have saturated Newton polytope. So one reason that having saturated Newton polytope is nice is that to see whether there is a non-zero monomial, that question is now same as whether that corresponding exponent vector is on this polytope. So that's one reason this saturated Newton polytopes are nice, and that's why we look at them. So in this talk, I want to focus on this family of polynomials called symmetric Grothendieck polynomials. And I will abbreviate it with SGP for the rest of the talk. So this is actually a generalization of a sure polynomials. And sure polynomials form a basis for symmetric polynomials, so they're very, very useful. And symmetric Grothendieck polynomials is just a generalization of it. So to define this, let's first consider x a vector with like m coordinates, and lambda be a partition with at most m parts. And we're going to let this L of lambda be a set of this pair where T is a semi-standard Young tableau of shape mu, and U is a row and column strict skew-Young tableau of shape lambda minus mu minus lambda, such that row R, the entries, such that row R has entries in 1 through R minus 1. So in here, a couple of things can I mention. Because of this, we need to have the mu is going to contain lambda. So in other words, if mu is going to be denoted with mu1, mu m, and lambda is denoted with lambda1, lambda m, where each of the coordinate represents like the number of boxes in row I, then we need to have the mu I is always greater than lambda I. And in fact, in row R, so like say mu R minus lambda R, well, because of this condition, this has to be less than or equal to R minus 1. So, yeah. So for example, if we were to look at, if we were to let m equals 3 and lambda equals 2, 1, then one possibility for mu is going to be 2, 2. So we're just basically adding one more box right there. And because this is the first row, we can only fill it with 1, since 2 minus 1 is 1. And this is a one possible semi-standard Young tableau of shape mu. So when I say semi-standard Young tableau, I just mean I'm going to fill this shape 2 by 2 with 1, 2, and 3 in a way that this is going to be increasing, but non-strictly, and this is going to be strictly increasing. So in here, when I say increasing, I just kind of mean like it's not going to decrease. Let's just say non-decreasing. That would be better. Non-decreasing. So another possibility is mu can be 2 to 1. So this is going to be the skew-Young tableau. So we can fill it with 1 here. We have to fill it with 1 here. In this case, we can fill it with 1 or 2. I just picked 2 in this case. And as you can see, it's strictly increasing this way, and it's just not increasing that way.
I have a quick question.
Yeah.
Can you remind me, maybe this is in your definition before, but are there restrictions on which numbers you're allowed to use for these tableaus when you're filling them in?
Yeah, thanks for mentioning that. This restricts the number of what you can fill these tableaus with. So if m is equal to 3, we can only fill it with 1, 2, and 3.
And does that mean that you could have just put a 3 in the spot where there's the 1 in the, or even in the first tableau, could have you just put a 3 in there, or?
I can put 3 here and 3 there, but I cannot put 3 into this spot because it has to be strictly increasing this way.
Yeah, I mean in the other one, the like shift, is it the shifted tableau? What's it called again?
The skew shape?
Skew shape, yeah. Is that
So,
allowed to be like a 3 or something?
So in skew shape, no, because in the skew shape, the only restriction on filling is this. So in the row R, the entries has to be between 1 and R minus 1.
Oh, okay. So that's not even a Young tableau. That's a, I mean it is, but it's like a separate.
Yeah, we have different feelings for both of them. Yeah. So in this one, we have that this has to be R minus 1, or at most R minus 1.
Okay. And does the filling in one row, does that matter for the later rows for the U? Or are they all just allowed to be whatever? Do they have this strictly increasing property?
Yeah, they have to be strictly increasing both column and row.
Okay, great.
Yeah.
Thanks.
Oh,
There's
you're
a
welcome.
comment just about the U tableau is also sometimes called a flagged increasing tableau or an elegant filling. Wen Chin Po said that, so thank you for that.
Thank you. Yeah, so if the mu happened to be, I'm going to write on it. If mu happened to be this, so this is lambda that we're crossing off, then this has to be 1, and this, in this row, we can only fill it with 1 and 2, but because it has to be increasing, we had to put 1 there and we have to put 2 there, and you can see that this actually strictly increased that way as well. So this will be the only possibility if mu was 2, 2, and 2. Okay. So if we, given these two things, if we let x be x1, x2, x3, then we let x to the power of t to be x1 to number of times 1 pops up. So in this case, 1 pops up twice, so we put 2 there. In this case, x2 2 pops up twice, so we raise it to the second power. And in this case, since x3 pops up like none of the 0 times, we raise it to the 0 power. And in this case, because x1 pops up twice, we raise to second power, x2 shows up once, so we just have x2, and because of those two, we have x3 to the second power. Okay. So given this, we can now define the symmetric Grothendieck polynomial. So a symmetric Grothendieck polynomial given of lambda, with at most n parts, is given by looking at all possible pairs and then multiplying this x to the t by -1 to the power of absolute value of u. So in this case, since u is just 1, we'll raise it to the first power, so we multiply by -1, and in this case, we just multiply by -1 squared. So given this, we have that the symmetric Grothendieck polynomial is equal to this giant polynomial. So let's actually break this down a bit. So you can see that this first 6th term, they actually come from mu of shape 2, 1. So these are the all possible fillings of this shape with fillings 1, 2, and 3. And the next 6, well, in this case, mu is going to be either the shape or the shape. And here, this is given by the shape, and that's given by this. And these are the all possibility for this mu. So we can actually look at this into, we can look at it just G into sum of some homogeneous functions. So this is all the ones that has degree 3. These are all the monomials that has degree 4. And these ones have degree 5, and this have degree 6. So, and when we look at this new polytope of this, we can actually kind of see this breakdown into degrees. So this point is the one that corresponds to degree of 6. The one right below is the one that corresponds to degree of 5. And this is the layer with degree 6. Yeah. No, this is the bottom layer. Sorry, this is the bottom layer. And this is the layer with this.
So there's a couple of questions in the chat before you go on. So one question is there no x1, x2, x3 term?
X1, x2, x3. Oh yeah, that is possibility that I forgot to put in there. Sorry. Yeah.
And then another question is, I'm confused about the role of lambda.
So lambda gives you all possible mu. So lambda is actually the, so in here, lambda is the one that's, when we go back to the definition of, sorry, I have to go back a lot. I don't know why, but it just happened.
I know we are asking a lot of questions, so if your talk goes a little bit longer than you expect, that don't worry about it because we got a lot there too.
Yeah. Yeah. Sorry, it's just like my. I think the drawboard PDF is struggling. So when we look at this definition, lambda, L of lambda, lambda is the one that kind of gives the base shape. And with mu, you can just kind of think of it as you can add one box to lambda in first row, two boxes to lambda in the second row. And that's how we can restrict this lambda. So this mu. So lambda gives like the base structure for this symmetric Grothendieck polynomial. And this lambda will always give you, sorry, I have to go forward more. This lambda will always kind of give you this, like the homogeneous part of the lowest degree. So, and as there was mentioned, there should be x1, x2, x3. So,
in fact, I think the comment from Martha Yip says that there should be a 2 times x1, x2, x3 maybe, but it's going to have the same Newton polytope either way.
yes, yeah. Okay. Yeah, there are 2, yes. Okay. So Escobar and Young proved that the symmetric Grothendieck polynomial has the saturated Newton polytope. So which means that every lattice point is going to be a content vector of some semi-standard Young tableau. So this actually, so that just means that like any lattice point on this Newton polytope is going to correspond to some shape of either this, and some feelings on this. And another property we look at with the lattice polytope is integer decomposition properties. So integer decomposition property is, well, we first need to look at the teeth dilation of a polynomial, of a polytope. So with the polytope, we basically just take all the points on the polytope and multiply that by t, and we look at the convex hull of this. We look at convex hull of this set, and that is the teeth dilation of P. And we say that P has integer decomposition property if for any positive integer t and any lattice point on that teeth dilation, there are t lattice points in the initial polytope such that they add up to this point. For example, this polynomial, a polytope we were looking at before has IDP. So if we look at the second dilation of this, so I just multiply everything by 2 and took the convex hull of that, you can see that 4, 3 is, wait, that's not 4, 3. 4, 3 is in the second dilation of the polytope, and that this can be written as 2, 1 plus 2, 2, which are the 2 points on the original polytope. So this doesn't always happen. So we wanted to show that for the Newton polytope of symmetric Grothendieck polynomials, this always happens. So one of the reasons why we care about IDP, or integral decomposition property, is that it plays a role in a conjecture about unimodality of H star vector. So given a polynomial, a polytope, an Ehrhart polynomial is basically the number of lattice points in each of the dilation. So Ehrhart series would just be the sum of these. And when we write this into rational function, the numerator is going to have degree d. So in here, this is p of dimension d. And the vector coefficient 1 and h1 star and all the way to hd star is called the h vector. So one of the common questions people ask about this is, when is this going to be unimodal? So there was one conjecture about this by Suzuki and Hibi. It says that if P is a Grothendieck polytope, which I will define later, that has integer decomposition property, then this is going to be unimodal. And there was another question. This isn't even a conjecture. This is a question. Is that if P has the integer decomposition property, is this enough to say that H star polynomial is going to be unimodal? So in our project, we wanted to classify more families that has IDP to look into these problems and look into these questions. So we have shown that the Newton polytope of a symmetric Grothendieck polynomial has integer decomposition property. In order for us to prove this, we wanted to look at the teeth dilation of this, and we were hoping that we can say that that's going to be a Newton polytope of another symmetric Grothendieck polynomial, because we know what lattice points of those symmetric Grothendieck polynomial Newton polytope of SGP are going to be. So we wanted to claim this, but that wasn't true. But they actually behave very nicely, and then we introduced this new polynomial called inflated SGP to look at the teeth dilation of the Newton polytope of SGP. So to define this, let's actually recall this L of lambda. And we're going to modify this. I don't know why that was blank, but that's fine. We're going to modify this. We're going to let H be a positive integer. And we're going to let, just so that I can write it better, I of H comma lambda be the set of U and T, where T is a semi-standard Young tableau of shape mu, and U is the row and column strict skew Young tableau of shape mu sub lambda, such that in row R, instead of having the entries be from 1 to R minus 1, we let it be 1 to H times R minus 1. So the inflated symmetric Grothendieck polynomial is very similar to just SGP, except we just let each of these rows to be H times R minus 1. So that's what this slide was about, but that was blank. So let's look at this example. So if we let M be 3 again and lambda be 4, 1, then if H is 2, now this is a possibility. Before, this wasn't a possibility because the second row could only have filling 1. So this wasn't a possibility before, so we couldn't have that when we were looking at SGP. But now that we're looking at inflated SGP where H is equal to 2, we can let this be 1, 2, and this is in I of 2, lambda. And if lambda is equal to 3, we can actually put 3 boxes in there. And this is still strictly increasing. So now this is a possibility as well. So inflated symmetric Grothendieck polynomial is defined very similarly to SGP. We just sum over all of this. And as you can see, if H is equal to 1, then this is the usual symmetric Grothendieck polynomial. Okay. So what we notice is that when we look at the teeth dilation of this, of a new polytope of this inflated symmetric Grothendieck polynomial, what we notice is that this is going to be the new polytope of this inflated symmetric Grothendieck polynomial. So in order for us to prove this, we showed that the vertex set of the two polytopes match. So we looked at the vertex set of this, and we looked at the vertex set of that. To look at the vertex set of those, we first needed to identify which ones are going to be the vertices of each of these polytopes. So in order for us to do that, we looked at each of the layers. And the way we define layers for this Newton polytopes are, we let small n be the size of lambda and big N be the largest degree. So the degree of the symmetric Grothendieck polynomial. And for each of the each of the integers between small n and big n, we let the hyperplane to be defined by all the coordinates equaling that number. And when we look at the intersection of this hyperplane and the Newton polytope, what we get is each of these layers that we were talking about before. And these layers actually corresponds to Schur, the Newton polytope of Schur polynomial, which we actually have already studied in the same paper. And then we actually have shown that all Schur polynomials have, or the Newton polytope of those Schur polynomials have IDP. So in here, we can see that there are a total of 4 layers. So here is like one layer, here's another, here's one, and here is another. And looking at each of these layers, we were able to, since these are all Schur polynomials, Newton polytope of Schur polynomials, we already know the vertices of these. So using that fact, we were able to identify all the vertices of just any inflated symmetric Grothendieck polynomial, and then we just compare the vertex set for these. And one other thing we looked at was we wanted to show the inflated symmetric Grothendieck polynomial also has SMP, so that each of the points on this corresponds to some kind of semi-standard Young tableau. And we were able to show that this actually, they do have SMP. And with that, we were able to show that the Newton polytope of ISGP has integer decomposition property for any H and any lambda. Brief sketch of this proof is that we look at a content vector. So since every point by this proposition is going to be a content vector of some semi-standard Young tableau. So for example, we can have something that looks like this. And what we do is that we, so in this case, like say T is equal to 3. So this is going to be a point, let us point on this polytope. And then because T here is equal to 3, we just take the first column and then put it there. Take the second column and put it there. Put the third column and put it there. And then just repeat 1, 2, and 3. And then we can divide this into smaller standard Young tableau. and they all happen to be in the original. They are all points in the original polytope. So we were able to claim this. So this is how we show that polytopes have integer, the polytopes of saturated Newton polytopes of inflated symmetric Grothendieck polynomials have IDP. Okay, so if you recall this conjecture, another thing that popped up is actually Grothendieck. So in this conjecture, P is Grothendieck and has integer decomposition property. And a lattice polytope is called Grothendieck if some integer, positive integer times this polytope is reflexive for some positive integer t. So what is reflexive? Well, a polytope P with 0 in its interior is called reflexive if the dual is also a lattice polytope. I'm not going to actually explain what dual is or much about this because this isn't the definition we used, because there is an equivalent definition. So equivalently, P is reflexive up to a translation if it contains a unique lattice point. So if it has a unique lattice point, and for any facets, so in here you can think of it as any of the sides, this distance is 1. So when it says here A is reduced, we just mean like get as small as possible coefficients. So in this case, the unique interior point is 2, 1. And there are facets here. So x1 is less than 3. So that corresponds to this. x2 has to be greater than or equal to 0. And so here, this is what we mean by A being reduced. Like there can be any coefficient in front of x2 here, but we pick the one that is smallest. And then we look at x2 has to be less than 2, and that corresponds to this, and that's this one. And we plug in this unique interior point into each of this equation, inequality. And when you plug in 2, 1 into x1, that's just 2. So 2 minus 3 is, has distance 1. So we know that, and we can check that for each of these hyperplanes. And they are all distance 1 away from the unique interior point. So this is actually reflexive.
I think I'm a little bit confused by the definition because, I mean, you're certainly thinking of a weird form of distance. Since what I want to say is that the distance between that diagonal line and the point P isn't 1 because it's like half the square root of 2 or whatever, like the shortest distance. So how do you get your distance exactly?
So
yeah, Andre says it's lattice distance. Is that the answer, that it's really just like the shortest distance along the lattice, not the shortest distance?
yes.
Okay.
Yeah, so we're looking at the lattice distance between the unique interior point and the line, yeah.
All right, thanks.
Okay. So we actually used this fact. We wanted to use, we used this definition of reflexivity to show that, show which inflated symmetric Grothendieck polynomial has reflexive Newton polytopes. So here are the list. So it's going to be reflexive if and only if H and lambda are one of these following. So in here, I'm not going to actually look at the details of this, but the idea of the proof was that we wanted to look at which we wanted to be able to identify all the facets. So we wanted to identify all the facets so that we can say that it is the lattice distance 1 away from the unique interior point. So first thing we had to do was like identify which ones will have unique interior points. And then out of those, we had to identify all the facets for those new polytopes. So in here, what we did was we noticed that, I'm going back to, where is that? I wanted to go back to the photo. Sorry, my computer is lagging a bit. So what we notice is that when we look at the facets of facet defining hyperplanes of this new polytope, that, so for example, it's really hard to tell, but like the top layer, what we notice is that it's going to be a facet of one of these Schur polynomial, on one of these layers, which are Schur polynomials. So in the same paper, we actually have identified all the facet defining hyperplanes of the Schur new polytopes of Schur functions using Rado's inequalities. So using the, since we already know what the hyperplanes are, facet defining hyperplanes are going to be for each of this layer, we use that hyperplanes to classify what are the hyperplanes that defines the facet of these inflated symmetric Grothendieck polynomials. So once we have found those, let me just go back to this. So once we have found those, we were able to identify all the inflated symmetric Grothendieck polynomials that have reflexive new polytopes. So that went a little shorter than I thought it would, but that's it. Thanks for listening to me, and here are my references.
Awesome. Let's thank Suji one of many times. I don't think anybody complains about a short talk.
That's good.
Yeah, thanks, Suji. Are there any questions from the audience? So you're getting a lot of thanks on the chat. Does anybody have a question? If not, I have a question. What other kind of polynomials can you play this game with, or do you think of playing with this?
So another polynomial, so I have mentioned the Schur polynomial. So that is another part of this paper, was that we looked at Schur polynomial, and when that's going to be, we have shown that it's going to be IDP, and then we have identified which ones are going to be reflexive. And another polynomial, actually Martha and Julie and I are looking at right now are Schubert polynomials. So Schubert polynomial is like another version of Schur function in, I don't understand the algebra side of it very well, but like I know that like it is another version of Schur polynomial. And we have, so there are actually, the Schubert polynomials have SNP. So there was like one paper by, I'm blanking on names, but they have identified all these, like how it's going to be SNP, and then using that we can show that it's IDP. So I'm like right now trying to show that which ones are going to be reflexive, but struggling with that, but I'm still looking at it. Somebody was asking about LLT polynomials. I actually am not familiar with LLT polynomials.
Stefan, do you want to unmute yourself and tell us what an LLT polynomial is?
I'm still starting to begin working with LLT polynomials, so you can get them if you look at border strip tableau instead of just classical semi-standard Young tableau. And apparently in my talk, Bruce was asking me later if I get something there with when I define my descent set on border strip tableau, and this is somehow related to LLT polynomials, and they are symmetric functions, generalizing Schur functions, but I'm still beginning with them, so I cannot give you a proper definition there.
I think that's maybe something worthwhile to explore.
Mhm.
Thanks for sharing that. Are there any other questions?
I just wanted to say that there's, I think Per Alexanderson, I don't know if he's here, has like some information on LLT polynomials and symmetric functions in general, but I will just add to the chat in case anybody is curious.
Yeah.
But it was a great talk. I don't have any questions. But.
All right, before we thank Suji one more time, let me remind you all that next week we will be back on regular time at 1 p.m. Eastern time. And our speaker next week is Marielle Supina from UC Berkeley, and she'll be talking to us about the universal valuation of Coxeter matroids from a polytopal view. And so we hope to have you all here next week. But let's thank Suji one more time.